The second complexity is something like order log n. So that's log of n. Okay? So you find this complexity in algorithms that have a bunch of divisions that happens one after the other. Let's say, for example, we have, let's try a sample algorithm. Let's say we have I takes this 10,000 number, so this is 10,000, and you're going to say while I is bigger than 0, we're going to replace I by I divided by 2, okay? And of course, this division is the Euclidean division. There is no remainder here. So if I say 3 divided by 2, I mean that's 1, okay? There's a remainder, but we just throw the remainder away. So this little algorithm would take how many steps in order to complete? Well, the 10,000 would be divided by 2, it'll be 5,000 by 2, 200, 2,500, and so on. So this algorithm always dividing I by 2. So the number of steps required is really the log of that 10,000. Okay? That's the binary log of 10,000. Because you can think of this in another way. We know that if you have some number, let's say, for example, 3, or let's say 2, for example. So if you have some number, and you keep multiplying this number by 2, by 2, by 2, many times, okay? So let's say we have multiplied this number by 2 n times, so this number would be 2 to the n, right? Because that's 2 times 2 times 2 n times. But if we keep this a lot of multiplications, we replace them by divisions, so it'll be 2 something, some constant x divided by 2, divided by 2, divided by 2, divided by 2, divided by 2. That's the opposite of a successive multiplication. So instead of multiplying by 2 n times, we're dividing by 2 n times. So that's the reverse operation of the 2 to the n. So the reverse operation of the exponential 2 to the n is log of n, okay? For that reason, if you take the log of this operation, you would get n. So my point is, whenever you find a bunch of division, successive division, every time you're dividing the original number by some constant, then the complexity would be log of that number, let's say this is b, log of b of n. That's the complexity, okay? We find this example in some very popular sorting algorithms such as merge sort or maybe quick sort, this dividing technique. And also we find this when we are looking for, let's say, for a specific number in an ordered array using binary search. We'll get to that later. So we said that our popular complexity, we have O1, we mentioned O log n, so that's O log n. There's also another complexity, very popular, which is order n. This complexity includes all the algorithms that require n operations in order to be computed. This is the most popular one. So for example, if you have an array, you want to print all the numbers of the array, then that would take order n, because you have to traverse every element inside the array. And if you're looking, for example, for, as we mentioned before, if you're looking for a number inside an array that is not sorted, then you have to traverse the entire array, you have to look for every number, then that also would take an order n complexity. Another very family of complexities that you have to know throughout your curriculum is the order n log n. Okay, we say that this is the super linear complexity. Basically, this complexity is a some operation that requires n operations, some algorithm that requires n operations. Every operation taken logarithmic time. So that's basically it. So let's say, for example, you have an array, a sorted array, and you want to always extract the minimum number of this array. You extract the minimum number, and that minimum number you want to print it out and remove it from this array. Okay. So let's say you can find the number in a log n time with binary search. So you keep well, let's replace the let's replace the array with a tree, because tree is more intuitive. Okay. So let's say we have a tree, and you're going to see this in data structures. So not a problem if it feels unfamiliar to you. So this tree has a bunch of nodes. Every node has a number. Let's say 4, 2, 3, 1, 1, 2, 3. All right, let's make it a binary search tree. So we have 2, we have 1. Here we have, let's say, 2.5, and here we have 7, here we have 6, and here we have 8. So as you can see here, this is a binary search tree where the left child is always less than the parent and the right child is always bigger than the parent. So if I'm looking for an element, then I have to always divide my tree into into 2 chunks, and then choose one chunk and throw out the other. So this searching for the minimum number would take a log n operation. But if we're interested in getting all the numbers, then we're going to repeat this operation n times, because we have n numbers, so that gives us order n log n. So that's a log n multiplied n times. Okay, so the first time we're going to get this minimum, we extract it from the tree, so that's log n. And then we get the other minimums. This one, we extract it from the tree, that's another log n, and so on, another log n. So we would keep that basically n times, so plus log n, plus log n. So these are repeated n times. So it'll be log n times n, okay? So that's the n log n complexity. This complexity is very popular because basically a lot of algorithms are based on top of this idea, the idea of divide and conquer, the idea of doing a logarithmic operation, but that operation is happening n times. And basically examples we can mention here, such as a lot of sorting algorithms like merge sort, and quick sort, and heap sort. All of these algorithms are order n log n. Well, quick sort, we said earlier that the average case is n log n. We don't care about the worst case because it's very rare to happen. Another type of complexity is basically the order n squared, or n to the constant. So this is called the polynomial. This is one type of polynomial complexity. So that's the complexity is just a polynomial. Basically, this one is when you have, for example, to search for all the triplets, the pairs. I'm sorry, all the pairs of things. Okay, let's say, for example, you have an array and you are interested in looking for all the elements that when you sum them together, you get another number. So one very simple algorithm to do this is to choose all the numbers Okay, choose them one by one, and whenever you select a number, you traverse the array again, search for another number that if you add it to this number that you chose at the first place, then you would find your number. Okay, so basically let's write an algorithm to demonstrate that, okay, to show you an example. So let's put it formally. So let's say you have an array 1, 2, 1, 3, 4, 7, 1. And let's say we're looking to find two numbers that when we compute their sum, we would take another given number. Let's say the number 7, for example. So in that case, we can take 3 plus 4 equals 7, so we would return true. Okay? If I give you, for example, 20, there's no two numbers that when you calculate their sum, you get 20. So in that case, you would return false. So here's a very simple algorithm to do that. So we start with an index. Let's call that beg. And another index that's, or let's call that number 1. So let's call that n1. And another index called n2, and we keep moving n2 and always taking the sum of n1 plus n2, seeing if that equals to 7. Let's say 7 is x. Okay, so the algorithm would be something like this: n1 takes 0, n2 takes 1, and the algorithm would be something like this. So for n1 starts at 0 up to the size of the array, which is n. And then inside it there is another 4. n2 starts at 1 up to n. If n1 is different to n2, it means that we're not on top of the same number. n1 is the index inside the array, and n2 is the index inside the array. They're not the same indices, so these are two different numbers. So if these two different numbers, n1, so if n1 plus, well, not n1, sorry. So let's do it in this same if statement. So if n1 is different to n2 and t of n1 plus t of n2 equals x. Well, in that case, we would say we would return true. Okay? So this is a simple algorithm that would do the job. But you know that this algorithm would have, for every number, we're going to traverse the entire array looking for another number to sum it with. So for every number, we're doing a linear operation. We're searching the entire array. So every number is being compared to all the other numbers. So we have here n operations, but also that n operations is being repeated n times. So that's n times n, which is n squared. For that reason, this algorithm is n squared. Okay, so we have, this is a constant operation, that if statement. We have here a for n equals to up to n, so this is a linear operation, so that's order n. And we have order n, and we have the outer loop, so that's for n from 0 to n, that's an order n, but an order n inside it there is another order n, so that's order n times order n times order 1, which is equals to order n squared. Okay, so this is an example of an algorithm that has complexity order n squared. So another complexity is order n cubed. Order n cubed basically searching for all the triplets of things inside a search space. So it's the same thing, but instead of 4 inside of 4, it'll be a 4 inside of 4 inside of 4, okay? Some k from 0 up to n, there's some j from 0 up to n, and here some I from 0 up to n. And we have here, let's say, a constant operation, okay? And 4, and 4, and 4. So you have the first one is order n, and the outer one is order n times order n, so that's order n squared. And the outer one would be order n times order n squared, so that's order n to the third. That's why how you can distinguish a complexity of an algorithm by just looking at it. Okay, and of course we're always talking about the worst case scenario, the worst case complexity. We're not interested about the best case complexity or whatever. There's also a type of another type of complexities. They're called the exponential complexities. It'll be something like this. So order some constant c to the power of n. So this is an exponential complexity. So for example, the Fibonacci's algorithm that we dealt with previously, we said that Fibonacci's of n equals the Fibonacci's of n minus 1 plus the Fibonacci's of n minus 2. The complexity of this algorithm is something like, well, it's 1.618 to the power of n. Well, we can think of that as order 2n, okay? We just round that up to 2. So the complexity of this algorithm is order 2 to the n. So that's an exponential algorithm. Okay? An algorithm that has an exponential complexity, time complexity. So it's horrible. Okay, this algorithm takes a lot of time to compute. All right. There's also another type of complexities, such as it's called the factorial. So the complexity is something like this. It's order n factorial. So this complexity requires n factorial time unit in order to compute a problem of size n. Now, basically, this has been an introduction to the complexity theory. Throughout the rest of the course, whenever we deal with a new algorithm or a new data structure or a new approach to solve a problem, we're going to make sure to always mention its complexity and how fast it is, and whether we should solve it like that, or whether there is a better approach to follow. So thank you for watching, and see you in the next video.